Hello, my name is John Whitson, and this is the Voice over IP, or VoIP, data extraction module. This is a part of New York University's Sci4 project. What we will cover in this module is a description of what the basics are for Voice over IP, or VoIP. We will also cover what protocols are used to control VoIP sessions on the internet. We also cover what data we can extract from the VoIP sessions within the limits of practicality, and also what are the limitations on what can be extracted. We'll also use some examples using Wireshark for the data extraction, and we're going to use the Natroba University harassment PCAP file that was recorded to discover and see what the VoIP session is in there as a way of recognizing them and analyzing them. And then there's a list of other resources available. What is VoIP? VoIP is, as I said, the Voice over Internet Protocol. VoIP replaces the analog telephone network by using the internet. Now, analog telephone network is usually your voice on an analog signal that goes over copper wires through a number of either mechanical or electronic switching systems. And this is the prevalent technology that has been used for a number of years until the internet came along, and the bandwidth on the internet actually became sufficient and reliable enough to transfer real-time voice data. So for a VoIP solution, the actual analog phone network is replaced with the internet, and what that means is the interface has changed too. Now, the traditional telephone interface now is replaced with IP phones. So instead of a 4-wire connector on the back, you now have a 6 or 8-wire connector on the back to carry your data representing your voice. And instead of an analog signal over copper, we actually have a sampled digital data representation of your voice going over the internet. Once digitized, your phone call is just more data to the internet. It doesn't really care what the content is as long as it's put in the right place at the right time. And VoIP takes advantage of that notion. The new interface, the IP phones, are essentially boiled down to a piece of software with a microphone and speakers that translates your voice and the network traffic going across it to and from audio, and managing the actual connection, the analogous function of dialing a telephone. In this case, VoIP also uses the use of email-like addresses besides telephone numbers. And in fact, in the Natroba case, we see they use telephone numbers, but if you use traditional free services that are available sometimes with VoIP, you can also use email addresses as if they were telephone numbers. And essentially, VoIP then uses the advanced routing capabilities of the internet and fiber optic networks and the high bandwidth that goes actually much faster than the old analog copper networks that were used for analog telephone to maximize the efficiency of the routing of the data. And there are a number of tools here. I mean, this is actually up on the right-hand corner what a Cisco IP phone looks like. It looks like an ordinary telephone. It's just that it's a lot smarter. It actually has better voice quality, and it has an Ethernet connector on the back. And one of the example software phones, or software SIP phones, is shown here as X-Lite, which is an IP phone application that provides you a window that looks just like a phone, but it is actually running under Windows on your desktop, and it uses your desktop hardware in order to implement the functions of a phone. And some of the other popular related to VoIP systems include Skype, FaceTime, Zoiper, and Session Talk. So, what protocols are used to control VoIP? VoIP can actually run either on top of TCP or UDP, and because of addressing, the actual data and layers at that level are transparent to IPv4 or IPv6, so it really doesn't care. VoIP can be run with or without encryption on the data and on the control lines. That actually has a very significant impact that we will talk about later. There are 3 protocols assigned to VoIP that are actually needed to execute. The first one is the Session Initiation Protocol, or SIP, which controls the setup and breakdown of the telephone call. Okay, endpoints in a telephone call actually have to register themselves so that their addresses and the path to their IP phone software is known publicly, and SIP is used to register and also to set up that call. On the analog phone network, that is essentially having your connection and the dial tone with the telephone company. The second one is the Session Description Protocol. Now, SIP will actually allow you to construct the network paths between a client, and two endpoints on the phone call. The Session Description Protocol says, here's how I'm going to transfer the real-time audio data. So it is actually contained as an addition to the SIP, so that SDP then tells you how you're going to transfer your audio, and that leads to the third protocol, which is the Real-Time Transport Protocol, which actually is the protocol to support the transfer of your audio data, your voice, as it's going back and forth over the phone call. There's another protocol sometimes that is used. It's called STUN, and it is because for most efficient routing, sometimes the address on the IP network, the public network, has to be known to a client that is protected by network address translation, so that it can in turn signal the other clients to allow the data to be routed properly. If you actually use a service in the middle, which is the example that we're going to be discussing, you don't need to worry about stun. But if you're going to do point-to-point messaging with your audio, which is more efficient, you will have to encounter some stun, but we're not going to cover that here. So the basics of SIP for VoIP: you need to have a couple endpoints, and we're going to refer to endpoint 1 frequently. The other endpoint, the other person on the other end of the phone call, could either be endpoint 2, which is an IP address, or it could actually be telephone network. Service providers do exist, and it's one of their major roles to connect the analog network to the internet phone network, if you will, through SIP providers. Okay. In general, endpoints do have to register with a SIP provider. Okay. Your SIP identity is used, and you register it with it so it becomes visible to people trying to call you so that you can advertise to them. Endpoints then initiate a call via methods to the SIP provider. So the actual mechanism is through a message called an invite message, or a method, and those methods actually instruct the SIP provider to break and make a connection to the different endpoints. Okay, the methods actually have to include the entity and the routing information for the call. There are two methods that are used to set up the call. The invite method starts the call, and the OK method actually contains information as to how to set up the real-time protocol. And the key message here is that the SIP client must interact with the provider in the middle. Here are the typical steps in a VoIP session. This is a standard activity diagram. If we go to the beginning, the endpoint 1 has to be able to register with a SIP provider, and then in this case endpoint 2 also registers with a SIP provider, and at a certain point then, in this case endpoint 2 is going to invite endpoint 1 into a call, and that's this line here. That invite message is then relayed by the SIP provider to endpoint 1 as an invite message with SDP data in it, and if that is successful, then the endpoint 1 will respond with a ringing message. So if the person on endpoint 1 is not registered, then an acknowledgement comes back that the person is not registered. But in this case, we get a ringing, just like a traditional telephone would ring, and the SIP provider echoes that status back to endpoint 2. And if on this case, if endpoint 1 picks up the phone call and answers it, then an OK message, including return information for the real-time protocol, configuration is returned here with SDP, and that is relayed back by the SIP provider to endpoint 2, so that endpoint 1 and 2 now know how to communicate back and forth. At that point, the audio begins, and the RTP data is streamed forward to the SIP provider and relayed back to endpoint 2. And likewise, the communication is both ways, the exchanging of the audio data, so simultaneously UDP packets with RTP are coming in with the actual audio data. And ultimately, one of the two parties will hang up. In this case, endpoint 1 is going to hang up, so endpoint 1 issues a SIP BY method, which is then echoed back to endpoint 2, and then there's an OK acknowledgement, and the call is over. This is an example now of a register request from Wireshark. What's important here is to note that the protocol is identified here as SIP. Okay, right? And all I had to do was essentially set the filter to say SIP so that it would only show SIP protocol in packets. You can see here in this case again from Nitroba, it is UDP. Okay, there is a session initiation protocol register method shown here. In this case, it happens to be with VonCP, which we believe translates back to a Vonage supplier. The method is register. You can see that there's a host and a port number. That's actually the control port number for the SIP service supplier, and you can recognize that once it's established for each of the suppliers. If you go down further in the message header, there's some information here as well, including a via method, which tells you how the routing works. Here in this case, it is from, who is calling from. This is a telephone number which is registered, and the actual to here is registered as well. Now in this case, it's the same telephone number. There's a special reason for that, and that's part of the challenge, so I won't actually go into it. Okay, you can see here that in the process we allow an invite, an acknowledge, a cancel, buy, notify, refer, options, update, etc. And in this case, there's also using a web proxy, so there is proxy information here to make sure that the user talking to the SIP service provider is authenticated. So this is an example of a register case, and you can see there's an awful lot of information in here unencrypted that you can see, including your source and destination phone numbers. Okay, the role of the session description protocol, SDP, again, it describes how to send the audio data in a VoIP session. That includes choosing what they call codecs, which are methods for encoding the audio data as digital data. Okay, there are a number of standardized codecs that are used in the industry. We're actually going to use the ITU G.711 one, which is a very old one for audio encoding. It's very popular, it's very established, and that makes it very useful to analyze. The SDP also tells you what the sample rate is, which is how many times they take a digital sample per second of the audio data. Obviously, a higher sample rate will give you much better audio quality, but also takes up a lot more bandwidth. For example, CD quality audio is taken at 16 bits and 44.1 kilohertz, which is 44,100 samples per second. The codec we're going to use actually uses data that has been compressed to 8 bits and is going to be using 8,000 seconds per sample. The companding method is a way that we pack the bits down for sample data. In this case, we're using a standard method called mu-law. Mu-law essentially allows you to take up to 14 bits wide of data and compress them down efficiently into 8 bits with minimum loss. It does lose data, but the loss is only in the very, very small difference values. It does not take have a loss issue with large difference values. The SDP also contains the real-time port protocol numbers for data exchange, and this is the only way to associate a particular RTP audio stream with a SIP session. That's kind of like the pivot number. So that's really important. Okay. SDP is only sent to SIP when an endpoint is ready to talk. So on the invite side, obviously it's immediately ready to talk, but the return values for that, when the receiving endpoint decides to talk, that's when it sends its SDP information. So SDP is not sent as part of the rings or busy signals that may come across as a part of the SIP protocol. Okay. Also, in the United States, typical telephony uses the ITU G.711 standard that we had mentioned earlier. It is an old one, but it operates at 8,000 hertz, which means there are 8,000 samples taken every second. And it originally is with 14 bits of magnitude, but it is compressed down through a thing called mu-law companding into 8 bits per sample with minimum loss. And this is acceptable for voice. It's not acceptable for music, but then again, hopefully you're not sending a lot of music over a telephone. Here's an invite example that contains an SDP record in it. Again, we filtered up here so that we're only looking at the SIP protocols. Here's the method called invite. Okay, and you can see the phone numbers are still hidden here in terms of identification. Okay, in this case, the content also includes SDP. And if you go down to the message body for the SDP section, you can see that there is a version number of the protocol, the IP address of who created it. The key line here is the media description line, which indicates that it's sending audio 150 here, 10050. That is the port number that the audio is going to be sent on. And the protocol also here is identified as RTP, which is the real-time protocol that we've been analyzing. Now, in addition to the basic codec that we have, which is number 0 here, pulse code modulation, mu-law encoded at 8,000 samples per second, in Natroba, the phone is capable of much better operations, but notice that they are all at this relatively slow audio rate. So this is where we are able to pick out the port and make sure the protocol and the codec used to decode that audio data can make sense for us. Okay, finally, when we actually want to look at the audio data, we're going to look with RTP. RTP also can run over UDP or TCP. RTP can only be recognized after an SDP session has taken place that identifies that port number. And that is a technique Wireshark uses. If you actually break into the middle of an RTP session, it will show you a stream of UDP packets of length 214 bytes. However, once it recognizes SIP has assigned a port number to that session, then it will then afterwards interpret any UDP traffic from that port number to be RTP. And in this case, for the G.2.711, okay, all the RTP packets are actually 214 bytes in length. If you subtract off the headers, which is 14 bytes for Ethernet, 20 for the Internet Protocol, 8 bytes for UDP, and 12 for the RTP header, that leaves 160 bytes of audio data. And if you were to divide our 8,000 samples per second into 160 bytes per packet, we come up with 50 UDP packets per second to carry your audio data. That's also meaning we're transmitting them out with our audio and our voice. That also means we're receiving 50 UDP packets per second to listen. The issue there sometimes is the TCP, which requires acknowledgments and whatnot, is too clunky for this kind of data rate. You tend to incur latencies and you get delays in your voice, which to an audio communication system like a telephone is unacceptable to users. So with UDP, we essentially can keep up the real-time stream without having penalties for losing packets in the stream. There's also a second part of this, in that RTP is set up so that if you lose a packet, particularly with audio data, it does not have a big impact on your transmission. The MPEG video standard uses the same approach, so that if you're streaming UDP between two endpoints and you happen to lose a dozen packets, you've only lost a little bit, maybe a click worth on the phone, and it's quite tolerable to actually understand the phone call when all that's going on. And in this case, we've identified that loss of each UDP packet is 2/100ths of a second, which is completely unnoticeable in the audio. You would have to lose an awful lot of UDP actually for it to be noticeable in the audio stream. Finally, the RTP packets are sequenced, so we know when things come in out of sequence, and have a unique identifier that is randomly assigned, because a lot of times in conference calls you can have a lot of talkers and a lot of receivers sharing the same RTP sessions, and in order to be able to identify which ones go with which, there is a 32-bit unique hexadecimal identifier that is used to sort which session goes with which. And finally, RTP really is ignorant of the format of the audio data. It just knows that it's got so many bytes to transfer and it's going to do so. So RTP will actually support any number of media types. It's just we happen to be looking at audio for the support of VoIP specifically. And again, with RTP and UDP, there's no acknowledgments, no retransmissions, just a streaming blast of data. And it is designed that way so that if you miss a piece of data, it doesn't actually impact the function that you were trying to provide. Okay, here's an example. This is a packet right out of Wireshark. And again, up here we've now said that we're going to filter on UDP, either receiving or transmitting port, being that magic RTP port number 10050. Okay, we can see it is actually UDP down here. Okay, in this case we're reading it on 10,050. You can ignore the name that's assigned with that port. That really has nothing to do with it. But in addition to the UDP, you can see we have a real-time protocol. There is a short header, including the version number. There's the payload type. Okay, in this case it's our G.711 pulse-coded modulation with mu-law encoding. There's a sequence number that says this is 20,915 in the sequence. Okay, there's a timestamp which tells you what the elapsed time is. This one, the synchronization source identifier, is the hexadecimal code that is used to filter the data. And after that header, here's the raw mu-law data. And in this case, it's a very quiet signal because a lot of the data is just sitting there with not a lot of change going on. So, what can we get from SIP? First thing is, just as a reminder, unlike point-to-point connections on the analog telephone network, all of this is available on the internet. Anybody who can tap across the routing path can pull out the PCAP packets that go along with your call. So there's access to identification information. Obviously, when we register with a SIP service provider, we register with an email or a phone number, or both, and those are fully visible. And you can get both sides of the phone call that way by looking at the SIP data. You also get client information. You can find out what software they're actually running to implement this if it's appropriate. Most importantly, we get the audio data. We can actually do that in Wireshark. We can decode and play the audio data from both sides of a conversation. And it is sufficient to actually perform analysis similar to what is done traditionally with telephone wire lap recordings. The difference is you don't need a court order to do this. You can just go out and sniff packets. You do have obligations on protecting privacy, but it is a lot more difficult to enforce. Status information. Even without completing a call, you can get indications of busy or that a client is actually valid, just not registered at the time. And another thing to remember is that the SIP provider who is hosting all this for you, they get to see all this too. So you could think of all the interesting people who would like to be SIP providers out there to capture all kinds of information that could be sensitive to you. One of the really easy things to do in Wireshark is to actually play the data from Wireshark. So the way you do that is you go into Wireshark, and on the top level menus you select telephony, and in the submenu you select VoIP calls, and that will search the packets and produce for you a table of all the conversations that are VoIP based calls, and in this case there are 2 that show up from the Natroba case. You then can click on the player button and use the decode button to process and turn the data into audio. And as you can see from the graphic plot here, there's a piece of audio going on, and that's what audio signal actually looks like. And you can actually listen to the conversation right in Wireshark. So next is, what are the limitations on the extraction of this kind of data? Well, obviously the first one, to protect privacy, is encryption. You can actually pay for services from a SIP provider to provide encryption of the SIP session. Over TLS, you can also use encryption to provide it over the real-time protocol, the RTP audio data. However, any conventional man-in-the-middle attack can undo this limitation by intercepting the TLS and the encryption standards for RTP. The other limitation, second one, is on commercial coders and decoders. Obviously, they do much better than the open and standard G.711 one, which really truly is very simple. However, there are proprietary ones that you would have to essentially work with a proprietary vendor to get access to those codecs, and those typically cost money, but you can get superior audio. And again, the better quality audio you can push through a smaller data link gives you both the reliability that you're interested in as well as the sound quality you're looking for. Okay, finally, limitations. It's kind of hard to reliably recognize a VoIP session if you don't have the SIP or SDP data. You can do it by looking at large numbers of, in this case, 214-byte UDP messages coming by at roughly an average of 50 per second, and you would recognize that as a real-time protocol client stream. However, you do not have any of the endpoint information to support that. So there is a limitation there. You kind of have to capture the teardown and breakup sequences in order to understand what it is you're listening to. And essentially that concludes the discussion on the module for VoIP. There's a list of additional resources here, and thank you very much.